Hello everyone, my name is Chris Fitzpatrick, and welcome to my Lab 5 presentation. So, the purpose of this lab was to predict and calculate the motion of a slinky dropped from rest. And I've got the video that I used, which I used in Tracker, in order to calculate where exactly the slinky dropped, and the fundamental physical principles were Newton's second law, the gravitational force, and drag force. And a summary of my findings was that the bottom of the slinky remains still until a certain time when the whole slinky moves together downward. Here's the video that I used for reference. So, for the data, measurements, and observations, the formulas that I used are the final velocity is equal to the initial velocity plus the net force times the change in time over mass. The net force is equal to the gravitational force plus the drag force plus the force of the slinky. Weight is equal to negative mass times gravity, and the drag force is equal to the negative magnitude of velocity squared times v hat. And the constants that I had were that the mass is equal to 0.25 kilograms, the initial position was 0.003, negative 1.2900 meters, and the initial velocity is 000 meters per second because initially the person on the right is holding it, and the change in time is 1.757 seconds between when it is in the air and when it hits the ground. So, as the top of the slinky met the bottom of the slinky, it continued to fall as 1. As you can see from the images that I have on the right, it starts out where it is completely suspended and the bottom of the slinky does not move at all as the top of the slinky falls, and then they join together as 1 down here in the second image. The motion of the slinky wasn't perfect as it would be compared to the predicted graph because there were other forces such as air resistance and other human errors or errors that happen in real life when conducting experiments in the experiment. And here is a very minimalistic graph of the motion or the position of the bottom of the slinky versus time. So at 1.1 seconds, the bottom of the slinky began to fall, and at approximately 1.7 seconds, the entire slinky hit the ground. And from 0 to 1.1 seconds, the bottom of the slinky remained in place as the top part of it fell down. So here is my coding. This is the baseline code that I used from Lab 2. And the counters that I used, or the counters that updated the code are velocity is equal to v initial plus f net times delta t over mass. Position is equal to initial position plus velocity times delta t. And the t is equal to t plus delta t, which just increases the time. And these are all based on the law of conservation of momentum and Newton's second law. So here is the first image of code. And then here are the second and third images of code. And here is my code in action in GlowScript. As you can see, this is my code, and let me run this program. And at the very end of it, it says, all done. And that concludes my presentation. Thank you all for watching, and I hope you have a wonderful day. Bye.